In the chemical kinetics, we have studied what is the chemical kinetics. Also now we are studying the integrated rate law for the various order of the reaction. In that we have derived the integrated rate law for zero order reaction. So now for the zero order reaction, the rate law was, or the value of rate constant was, K is equal to 1 upon T into bracket concentration of reactant at initial level minus concentration of reactant at time T. This was the equation for rate constant of zero order reaction. In the next point we have discussed it for the first order reaction. So now for the first order reaction, the K is equal to 2.303 upon T into log of initial concentration of reactant upon the concentration of reactant at time T. This was the equation for the first order reaction. In the previous lecture we have studied for the second order reaction. So now for the second order reaction there are two cases. The case 1, 2A gives the product P. Okay. For such type of reaction, the K was equal to 1 upon T into the bracket 1 upon concentration of reactant at time T minus 1 upon concentration of reactant at initial level. Okay, here I have taken A because here reactant is A. So now in the today's lecture we are going to discuss for the case second. For the case second, that is A plus B gives product. For such type of reaction, the reactants are not same. So the equation for such type of reaction is equal to like this. K is equal to 1 upon T into bracket B minus A ln A B minus X upon B into A minus X. So this is the complicated one. This can be studied like this. Now for the case 2, that is A plus B gives the product P. So here we will define some term when T is equal to 0. That means at the initial level the concentration of A will be A naught and concentration of B will be equal to B naught. At time T, the concentration of A will be equal to A naught minus X or A at time T. Okay. Similarly for the B will be initial minus some quantity x, or it can be denoted by bt. So this is, in some books it is denoted by like this, in some books it is denoted by at, and in some books it is denoted by small a minus x, and here small b minus x. Okay, and this a, it could be denoted by small a, and this as a b. So the integrated rate law or the equation of rate constant for the second case of second order reaction is like this. K is equal to 1 upon T B minus A ln of A into B minus X upon B into A minus X. This is the equation for rate constant of second order reaction when the two reactants are different. Okay. So now we will study for the third order reaction. So in the third order reaction, that is A plus B plus C gives the product P. So now when A is equal to B is equal to C, this we can write 3A gives the product P. Now from this we can derive minus dA upon dt will be equal to K into concentration of A cube. So now we will transfer the terms dA upon A cube, which is equal to minus K dt. Okay. Integrating on both the sides, that is integration initial concentration A naught to the concentration of A at time t dA upon A cube. Okay, which is equal to integration from t is equal to 0 to time t minus K dt. So now the integration of this will be like this. Concentration of A raised to minus 3 plus 1 upon minus 3 plus 1, and the integration limits from A naught to A t. This minus K outside integration of dt is t. The limits from 0 to t. Okay. Now solving further, A raised to minus 2 upon minus 2, the integration limits as it is will be equal to minus K t. Okay. So this minus 1 upon 2, this we can take outside the bracket. And instead of writing A raised to minus 2, we can write 1 upon A raised to or A square. Integration limit will be like this. which will be equal to minus kt. So this minus sign from the left hand side, from the right hand side gets cancelled, and putting the integration limits, we get 1 upon at square minus 1 upon a naught square bracket close, which is equal to kt. Therefore, k is equal to 1 upon 2t into the bracket 1 upon at square minus 1 upon a naught square. Okay, this is the equation for third order reaction. So now we will study the half life time of third order reaction. So the equation was k is equal to 1 upon 2t, 1 upon concentration of A at time t square minus 1 upon concentration of A naught square. So at t or a half lifetime, the AT is equal to half of the initial concentration. So now we will put the value. K is equal to 1 upon 2t, 1 upon this A naught upon 2 square minus 1 upon A naught square as it is. So 1 upon 2t is equal to 2 square is 4 upon A naught square minus 1 upon A naught square. So 1 upon A naught square, this can be taken as common outside the bracket. 1 upon 2t into A naught square into bracket 4 minus 1. So which is equal to 3 upon 2 t into A naught square. So therefore t 1/2 is equal to 3 upon 2 k into square of initial concentration. Okay. So now we will study the generalized rate law for nth order reaction. So for the nth order reaction, minus dA upon dt, that is change in the concentration of reactant with respect to time, will be equal to k into A raised to n. Why n? We are studying for the nth order reaction. So therefore dA upon A raised to n is equal to minus k dt. Here integrating from A naught to A t, dA upon A raised to n minus k common or constant, integration from 0 to t dt. So now this answer will be a raised to minus n plus 1 upon minus n plus 1. The limits will be a naught to a t, which is equal to minus k t. So now this 1 minus n we are taking outside and putting the integration limits. N minus 1, the limits are from a naught to a t, which is equal to minus k t. Now this 1 upon 1 minus n giving the integration limits a t raised to n minus 1 minus 1 upon a naught n minus 1, which is equal to minus k t. Therefore, k is equal to minus 1 upon 1 minus n t, this bracket as it is, so emerging this minus sign, here we can write n minus 1 t if you will put the value of n in this equation, you are able to find the value of k of various order reaction. This is the generalized equation for the rate constant of nth order reaction. But here there is one exception, that this is not applicable for first order reaction. Okay, so everyone has to remember that this equation is not applicable for the first order reaction. Okay, the next part that we are going to study is effect of temperature on reaction rate. So in this we commonly know that increase in temperature has increased the rate of chemical reaction. So here there is one term, that is the temperature coefficient. So the temperature coefficient is the ratio of, the rate constant of a reaction at two temperature differing by 10 degree Celsius. So temperature coefficient is the ratio of rate constant of a reaction at two different temperature differing by 10 degree. So for example, temperature coefficient is equal to the ratio of rate constant. Okay, it is the ratio of rate constant. What is the term of rate constant of a reaction at two temperature differing by 10? So for example, if this is 35 degrees Celsius and at 25 degree Celsius, so that is K 35 upon K 25. This is known as a temperature coefficient. So now we will study the effect of temperature. The rise in temperature increases the speed of reaction. This can be explained by the collision theory. By the collision theory. According to the collision theory, for the reaction to occur, there must be collision between the reactant. So, for the reaction to occur, there must be the collisions between the reactant. Okay, so according to the collision theory, for the reaction to occur, there must be the collision between the reactant molecules. Most of the collision occurring between the molecules are ineffective. That means there are the collisions but that are ineffective to convert that reactant into the product. So the important postulate is that the collision results in the chemical reaction in which the colliding molecule are associated with the certain minimum energy called as a threshold energy. So that we will write here. The only collisions result in chemical reaction, that is formation of product, in which the colliding molecule have some or certain minimum energy known as threshold energy. Okay, known as threshold energy. So that now according to the collision theory, first is for the reaction to occur, there must be the collision between the reactant molecules. But not each and every collision results into the formation of product. So the collision in which the colliding molecule have minimum energy, that is the threshold energy, that molecule gets converted into the product on the collision. So if we have to remember these two postulates of the collision theory. So what happens as the temperature changes, energy distribution changes. As the energy of molecule increases, consequently the rate of reaction, which depends upon the number of effective collision, becomes or it increases, and due to that it results into formation of product. That means as we increase the temperature, the colliding molecule gains some energy, and due to some energy the collisions between them results into the formation of product. So the most of the molecule having energy less than kinetic energy or the threshold energy, this could be explained like that. See, if these are the colliding molecules, if we supply or we increase the temperature, what happens? This molecule gains some energy, and due to that energy the molecule's energy gets increased, and due to that the collision results into the formation of product. That means it results the chemical reaction. So the colliding molecule have some kinetic energy in them. That means the colliding molecule has the kinetic energy. So to reach the threshold energy, the energy must be supplied to that colliding molecule. So the energy which is required to reach the threshold energy in order to reaction to be happen is known as activation energy. That means the excess energy required to reach threshold energy in order to react is known as activation energy. So here we can write it like this: the threshold energy is equal to that kinetic energy that is already possessed in the reacting molecules plus the activation energy. Okay. So here I will draw one graph or one diagram. This is the energy. Here the reaction coordinate. Suppose this is the reactant or the energy of reactant. So reactant to be get converted into the product, it must cross the energy barrier. That is like this. Okay. So this is the energy barrier. Okay. So now this is a threshold energy. So the energy required to the reactant to reach threshold energy is known as activation energy. It is the activation energy. Okay. So the energy required to the reactant molecule to reach the threshold energy is known as the activation energy. Okay. So as we supply the temperature, the reactant gains some energy, and as the reactant gains some energy, the required activation energy becomes less. So the rate of reaction gets increased. So as the temperature increases, the reaction rate increases. So this is best explained by the Arrhenius equation. Arrhenius equation is the equation which denotes the effect of temperature on the rate of the reaction. It is like this: K, that is rate constant, is equal to A into e raised to EA upon RT, where K is rate constant, A is Arrhenius pre-exponential factor, or we can say frequency factor. Where EA is activation energy, R is gas constant, and T is temperature. Okay, this is for the Arrhenius equation. In the next lecture, we are going to rearrange this Arrhenius equation at different temperature, and also we are going to solve some numericals based on the Arrhenius equation. So here we will stop. Thank you.